Tonight you are going to Mars. Not to look at it through a telescope. Not to plant a flag, collect a few rocks, and pose beside a lander while Earth watches on delay. Not to begin a shining new civilization beneath a glass dome. For now, your objective is considerably less glamorous. You are simply trying to make sure Mars lets you come home. You are one of the first 4 human beings assigned to land on the Red Planet. The journey out may take months. The stay on the surface may last more than a year. The return may take months again. During all of it, Earth and Mars continue moving around the Sun, creating brief opportunities when a spacecraft can travel between them without demanding impossible amounts of propellant. Landing is only the middle of your mission. Before you get comfortable, take a quick moment to like the video and subscribe, but only if you genuinely enjoy what we do here. Now dim the lights, pull the blanket up, and settle in. You are currently inside an atmosphere you did not have to manufacture, on a planet that does not require a launch window before it allows you to go home. Tonight, that counts as luxury. Let us pause for a moment. What could trap the first humans on Mars forever? Would the ascent engine refuse to ignite? Could the machine producing your rocket oxygen fall behind? Could a global dust storm switch off the base? How long would recycled air, water, and food support 4 people when every replacement part was on another planet? What would happen if the best surgeon available was a radio message 20 minutes away? If you missed the departure window, would you wait a few days or more than 2 years? Could mission control still guide you home? Why could Earth not simply launch a rescue mission? And at what exact point would a planned stay become a life sentence? Those questions are not predictions. No serious Mars mission would be designed around abandoning its crew. Return hardware may be sent ahead. Propellant may be delivered or produced before the astronauts leave Earth. Launch rules may keep you on the ground until the route home has been verified, as far as any unflown interplanetary system can be verified. Congratulations. You survived the launch. Earth is already falling away behind you. Mars is still months ahead. And the first machine deciding whether you will ever come home is not inside your spacecraft. It is already waiting on Mars. It is your return vehicle. Long before your crew walks to the launch pad, an uncrewed cargo mission departs without you. Depending on the architecture, it may carry a surface habitat, power units, food, spare parts, a rover, communications equipment, an ascent vehicle, ascent propellant, or machines intended to make that propellant on Mars. Another spacecraft may deliver the vehicle that will wait in orbit to carry you back toward Earth. There are many possible designs, and no final architecture described here should be mistaken for a booked flight plan. The important principle is simpler. Equipment can take risks before people do. Imagine watching the cargo land from a control room on Earth. It does not arrive neatly beside a painted line. Mars has no runway crew waiting with illuminated batons. An autonomous vehicle enters the atmosphere at enormous speed, trades that speed for heat, drag, lift, parachute forces, and rocket thrust, then tries to place many tons of machinery near a site selected years earlier. After touchdown, it must wake itself, inspect itself, communicate across interplanetary distance, and perhaps unfold an entire base. If the mission depends on local propellant production, the work may begin before you launch. Carbon dioxide makes up most of the thin Martian atmosphere. A machine can draw that gas inward and separate oxygen from it. NASA's MOXIE experiment aboard Perseverance proved this basic process at small scale, producing oxygen during a series of tests in different Martian conditions. That was an important demonstration. It was not a human return plant. A crew ascent system may need oxygen in industrial quantities. The oxygen must be produced, purified, liquefied, transferred, stored at extremely low temperature, measured, and kept available until launch. If the ascent engine uses methane and oxygen, The architecture must also provide the methane, or manufacture it from resources that may include hydrogen delivered from Earth or water acquired on Mars. Each choice shifts the mass. Power, equipment, site, schedule, and risk. The attractive phrase is living off the land. The less romantic phrase is operating a remote chemical factory on a planet no technician can visit. Your mission rule may require that the ascent propellant be ready before you depart Earth. That turns the factory into a gatekeeper. If production is slow, your launch waits. If a compressor fails, your launch waits. If telemetry suggests contamination in a tank, your launch waits. Delay is painful and expensive, but it happens while you are still standing under a blue sky with hospitals, warehouses, and breathable air nearby. This is the first great safety transformation. A failure that would strand you on Mars becomes a postponement on Earth. The same logic applies, even if the propellant comes entirely from Earth. Mission planners may send the fueled ascent vehicle ahead and verify its condition before committing the crew. Delivered fuel avoids depending on local resource extraction, but it increases the mass that must be launched from Earth, carried across space, slowed at Mars, and landed without damage. In most proposed architectures, ascent propellant is among the largest categories of mass placed on the surface. Mars charges a transportation fee for every kilogram, and it accepts payment only in more spacecraft and more propellant. That is why return hardware has such strange power over the rest of the mission. Add a kilogram to the cabin that rises from Mars, and you need more ascent propellant. More propellant may require larger tanks and engines. Those additions increase the mass that must land. A heavier lander requires more capability during entry and descent. All of that equipment had to leave Earth in the first place. One innocent kilogram can send demands backward through the architecture, like a rumor through a very anxious office. Round trips are not simply one-way missions performed twice. They are systems in which the final climb affects almost every earlier step. For months or years, the pre-deployed base operates without a human hand. Power flows. Heaters keep vulnerable hardware within acceptable temperatures. Computers monitor pressure and state of charge. Dust settles where the design hoped it would not. Seals age. Radiation passes through electronics. A small anomaly appears, disappears, and returns. Engineers on Earth study trends and decide whether the green return light deserves to remain green. They are trying to prove a negative, that no hidden failure is waiting for the moment you need the system most. They cannot prove it perfectly. A rocket sitting on Mars cannot be test-fired in its full mission configuration without using the very system it must preserve for you. Some components can be exercised, valves can cycle, circuits can be checked, tanks can be monitored, software can simulate procedures. Yet every launch vehicle contains events that happen only once. At some point, verification ends and trust begins. You have not even launched, and your escape already depends on a machine aging millions of kilometers away. This sounds alarming. It is also safer than arriving first, and hoping to build the way home afterward. The distinction will matter later, when we ask what a rescue can realistically carry. For now, every healthy signal from Mars buys confidence. Every kilogram of stored propellant buys possibility. Every spare part placed near the habitat changes a future emergency from impossible to merely unpleasant. Finally, the mission readiness review arrives. The habitat is functioning, surface power is stable, communications links are healthy, the ascent vehicle reports acceptable status. If local propellant production is part of the design, its tanks have reached the required level with reserve. The orbital return system, if pre-positioned, is waiting. On your console, the line stays green. Only then do you climb into the vehicle on Earth. You survived the first test of your return system. You have not left Earth yet. Now the part of the mission carrying people must begin. At launch, danger is loud enough to be understood. Engines ignite, structures vibrate, acceleration presses you into the seat. Tens of thousands of people have spent years trying to ensure that the violence beneath you remains controlled. For a few minutes, the mission is a tower of propellant turning itself into altitude and speed. Yet early in the journey, contingency options still point toward Earth. Depending on vehicle design and mission phase, an abort might place you into orbit, separate the crew vehicle, or bring you toward a recovery zone. Even after reaching space, you may spend time assembling, fueling, checking, or waiting in Earth orbit or near the Moon. A fault discovered here can end the mission without ending the crew. That is not failure in the tragic sense. It is the system doing its job. The decisive moment comes when the spacecraft commits to interplanetary flight. Engines burn, velocity changes, and Earth begins to release you. Popular language often says there is no turning back, but orbital mechanics dislikes absolute statements. Some trajectories offer abort paths. Some problems occur early enough for a free return or modified return. Future propulsion systems could change the options. Still, none resembles pulling onto the shoulder of a road. A return may take months, demand major propellant reserves, or expose the crew to conditions the habitat was not meant to support. Once the departure burn ends, Earth is no longer the place beneath you. It is one moving destination among two. The first days are busy. The crew checks seals, deploys equipment, configures life support, confirms navigation, and begins exercise routines. Small objects find their preferred corners in microgravity. Your body redistributes fluid toward your head. Your inner ear negotiates with a world that has stopped providing down. The fan noise becomes the acoustic floor of existence. Listen to it. The fan is not ambience. It is circulation. Without moving air, the carbon dioxide you exhale can collect around your face in microgravity, because warm breath does not rise in the familiar way. Ventilation carries cabin air towards sensors and scrubbers. The steady mechanical sound says the atmosphere is being mixed, cleaned, cooled, and returned. Silence would be information. Your transit habitat is not a sealed can containing 3 years of fresh air. It is a processing plant wrapped around 4 mammals. You consume oxygen and produce carbon dioxide, water vapor, heat, urine, solid waste, trace gases, crumbs, fibers, hair, skin cells, and endless opportunities for filters to become less efficient. The environmental control system recovers water, removes contaminants, manages humidity, generates oxygen, and keeps pressure within limits. The cleaner the loops are, the less replacement mass must be launched. But recycling is never a magic circle. The International Space Station can recover much of its water, and its systems have taught engineers an extraordinary amount about regenerative life support. The station also lives comparatively close to spare parts, specialists, and cargo vehicles. On the way to Mars, every pump you may need is either already with you or still on Earth. The question is not only whether a component is reliable, it is whether it can fail in a way you can diagnose, reach, isolate, repair, or bypass with the tools and materials aboard. This changes the meaning of maintenance. You are not simply keeping a spacecraft tidy. You are slowing its transformation into an inventory of worn components. Each replacement part has a mass. So does each tool. So does the packaging protecting it from launch vibration and years of storage. You cannot carry a complete second spacecraft in labeled drawers. Instead, engineers study failure histories, model probabilities, redesign weak components, create redundancy, standardize parts, and teach the crew to manufacture selected items. The result is not immunity. It is a carefully shaped field of recoverable failures. Then there are failures the crew cannot repair with a wrench. Outside Earth's magnetic protection, radiation becomes a persistent part of the mission. Galactic cosmic rays arrive from beyond the solar system with energies that make shielding difficult. Solar activity can produce particle events that raise exposure sharply over shorter periods. The spacecraft may use supplies, water, food, and dedicated material around a small shelter so the crew can move into greater shielding during a warning. Radiation is not usually a dramatic beam crossing the cabin. You may feel nothing. That is part of its narrative cruelty and scientific reality. Exposure adds risk over time. It can damage cells and may affect multiple body systems. A large solar particle event creates an acute operational problem. The background environment creates a cumulative health problem. They are related, but they are not interchangeable. You cannot repair cumulative dose. You can only manage what comes next. Every transit day also changes your body through microgravity. Exercise helps reduce losses in muscle, bone, and cardiovascular capacity. But exercise consumes crew time, power, equipment life, water, and volume. A broken exercise device is not merely an inconvenience. Months later, it may influence how safely you can work in a pressure suit, climb inside a vehicle, respond to an emergency, or tolerate another gravity transition. This is how Mars begins to trap you before you arrive. It does not close a door. It spends your margins. 1 month into the journey, Earth still looks unmistakably like a world. Later it becomes a bright point. Messages from home take longer to arrive. A question and answer separate into different parts of the workday. The crew receives news, recorded conversations, technical guidance, and private communications, but not presence. No one can place a hand on a warm panel. No expert can physically take your tool and show you the angle they mean. Mission control gradually changes from a voice in the room to a correspondence with a brilliant, distant institution. The spacecraft continues to age. So do you. A sensor drifts. A valve takes slightly longer to move. A water processor requires a procedure no training simulation made memorable. You and your crewmates spread diagrams across screens, compare telemetry, record each action, and send the complete log toward Earth. The answer will come after you have already made the first decisions. The repair works. That is good news. But it opens the next problem. Your mission has now used a spare that was intended to cover the rest of the round trip. Nothing dangerous is happening. The display is green, yet the same failure, if repeated, will have a different meaning because the inventory has changed. Risk is not only the chance that something breaks, it is the condition in which the next break occurs. By the time Mars grows from a star into a disk, you understand this instinctively. You have survived launch, departure, radiation alerts, bodily adaptation, and thousands of hours of mechanical life. The planet ahead is no longer an image. It is a destination with gravity. To reach the surface, your spacecraft must trade interplanetary speed for a landing gentle enough to leave the return journey intact. And Mars has never been asked to catch anything like your home. You survived the journey to Mars. The return vehicle is waiting below. The surface is waiting with it. And before either can help you, Mars has to catch a human-class lander far larger than any payload successfully placed there so far. Every successful Mars landing can make landing on Mars look almost routine. A heat shield glows, a parachute opens, rockets fire, a machine settles into red dust and sends a signal home. The sequence fits neatly into an animation because the failures that did not happen are invisible. Your lander is different in scale. NASA's flown robotic entry, descent, and landing systems have placed payloads of roughly a fraction of a ton to about 1 ton on the surface. Human-class concepts require landed masses above 20 tons, depending on architecture. The exact figure is not our concern here. The gap is a vehicle carrying people, habitat volume, life support, power, supplies, and ascent-related hardware cannot simply be a rover capsule enlarged with the corner handles dragged outward. Mars has enough atmosphere to create severe heating and aerodynamic forces, but too little atmosphere to make a large payload easy to stop with parachutes alone. That awkward middle ground shapes the descent. The vehicle may use a large, rigid or inflatable heat shield, lift to steer through the atmosphere, powerful engines for supersonic retropropulsion, or some combination. Each design must manage transitions between regimes while navigating toward a safe site. You enter inside a machine that cannot be fully flight tested on Earth under identical conditions. Earth has the wrong gravity, atmosphere, pressure profile, chemistry, and landscape. Engineers use simulations, wind tunnels, arc jets, vacuum chambers, subscale flights, component tests, and data from robotic Mars missions. They can build confidence. They cannot place a full human Mars lander into a duplicate Mars on Earth and try again next Tuesday. That makes your descent the final experiment in a long chain of evidence. Hours before atmospheric entry, the crew checks pressure suits, seats, displays, communications, and emergency supplies. Loose objects are secured. The vehicle separates or configures for entry. Navigation updates its position and velocity. Mars fills the view. Although the view may soon become irrelevant behind shutters, structure, glare, and concentration, the atmosphere begins as almost nothing. Then, it is heat. Plasma around the vehicle may affect communications. Guidance commands the craft to bank, using lift to control range and heating. The landing target is more than an empty patch. It is part of a surface system. Land too far from the pre-deployed habitat, and your spacesuits may not have the consumables to walk there. A rover can cover distance only if it is available, healthy, and able to reach you. Land near the base, but strike a boulder, steep slope, or soft terrain, and accuracy becomes a beautifully precise way to arrive at the wrong outcome. Terrain relative navigation compares what sensors see with maps prepared from orbit. The vehicle identifies hazards and adjusts. Meanwhile, velocity remains the central fact. You are still moving too fast to belong to the ground. Engines ignite while the craft is descending through the Martian atmosphere. Their plumes interact with gas, dust, and regolith. At human scale, those plumes can excavate material, obscure sensors, sandblast nearby equipment, and turn the landing site itself into a moving hazard. Pre-deployed power systems and habitats may need distance or shielding. Distance then demands cables, vehicles, time, and navigation after touchdown. Every safety choice creates another interface. The final seconds are not silent. Pumps, engines, structure, warnings, callouts, and breath fill the cabin. Mars rises toward you on a screen. Velocity falls. The landing gear absorbs what remains. Then the numbers stop changing. For a moment, no one moves. The lander leans under a gravity only about 3/8 of Earth's. Dust drifts through air too thin to carry it with terrestrial force, yet capable of keeping fine particles suspended. The engines shut down. Fans continue. You have landed on Mars. This is usually where the story ends. For you, it is where the return countdown becomes local. Congratulations! You survived the landing. The ascent vehicle is still outside. Earth is now a moving point somewhere beyond the sky. And the first thing Mars offers you is no help at all. There is gravity, but not enough to hold a breathable atmosphere. There is water, but much of it is frozen, buried, bound into minerals, or mixed with substances you do not want in a cup. There is carbon dioxide in abundance. But abundance is a peculiar word for an atmosphere whose surface pressure is less than 1% of Earth's average at sea level. There is sunlight, but less of it. There is land in every direction, but nowhere you can stand without equipment. Your base is an argument against the planet. Pressure vessels insist that air remain dense around you. Heaters insist that water stay liquid and electronics stay within operating limits. Filters insist that dust stop at the airlock. Power systems insist that night, weather, and distance are administrative details. A habitat on Mars is not a building in the terrestrial sense. It is a spacecraft that has agreed to remain in one place. Before anyone opens an outer hatch, The crew verifies the route to shelter. If you landed close enough, you may connect the lander to a habitat through a pressurized tunnel or cross the ground in suits. If the architecture uses a pressurized rover, it may meet you or wait nearby. The details vary, but the rule remains: do not leave one working pressure vessel until you know how to enter another. The habitat has been awake for months or years. It contains air, stored supplies, displays, sleeping stations, exercise equipment, a medical area, hygiene systems, tools, and the unmistakable smell of materials that have been sealed together without human noses present. It may feel spacious compared with the lander and cramped compared with any room on Earth. Both impressions are correct. You close the hatch behind the last crewmate and listen. The fan is running. Pressure is stable. Oxygen is within limits. Carbon dioxide removal is active. Fire detection is healthy. Water is available. Power reserves are acceptable. The first meal on Mars comes from a package assembled years earlier. You add warm water that has already lived several lives inside the mission. Some of it crossed space in a tank. Some was recovered from cabin humidity during transit. Some recently passed through a crewmate. Chemistry has no sentimentality about origin. You lift the cup, it is ordinary water, which is the highest compliment engineering can receive. Outside, the temperature is hostile, the pressure is near vacuum by human standards, and the atmosphere is mostly carbon dioxide. Inside, you complain that the water is slightly too warm. Civilization has arrived. The first surface day is not devoted entirely to flags and panoramas. You inspect the systems that must keep working while Mars moves through its seasons. You confirm the ascent vehicle's status from the surface. You inspect data from power units. You inventory emergency oxygen and water. You check radiation shelter supplies. You compare the actual state of the base with the version you rehearsed on Earth. Small differences matter. A cable lies where the map shows open ground. A seal closes but requires more force than expected. Dust has formed a fine line at the base of an outer interface. One power unit produces slightly less than its predicted output. None of these is a crisis. Together, they announce that your simulation has ended. Your first excursion begins with ritual. Suit cooling, oxygen, communications, battery, pressure, leak check. Every glove must remain both flexible and airtight. Every connector must work through layers. The suit is not clothing. It is a one-person vehicle, and the person inside is also its most irregular moving component. When the airlock pumps down, the sound changes. The habitat remains on one side of a pressure door. Mars waits on the other. You open the outer hatch and place a boot onto the surface. Dust compresses beneath you. The lower gravity changes your balance, but the suit's mass still resists acceleration. A tool does not become weightless. It becomes lighter while retaining its inertia. Your body has spent months adapting to microgravity, and now the planet asks it to walk while wearing a stiff pressure vessel. The work is slow. You inspect external connections, collect images, verify navigation markers, and approach the ascent vehicle only within approved limits. Nothing about the rocket looks heroic at close range. It looks like plumbing, thermal blankets, structure, access panels, and surfaces that must not be damaged. Its engines will eventually need to take your crew from the ground to orbit. Today, the most useful thing you can do may be to photograph a connector and confirm that a protective cover remains where it should. Back at the airlock, Mars tries to come inside with you. Dust clings to boots, joints, fabric, tools, and sampling containers. Procedures remove as much as possible before repressurization. Some habitat designs may keep the suit outside using suit ports, allowing an astronaut to climb through the rear of the suit. Other systems may use air showers, brushes, electrostatic methods, dedicated dirty zones, or combinations. No technique makes dust stop existing. The red line at the airlock is partly visible and partly conceptual. On one side is the planet. On the other is the machinery keeping the planet out. That evening, after health checks and system reviews, you receive Earth's reaction to your landing. The celebrations happened long ago from your perspective. Images of crowds arrive, family messages play. Mission Control sends a carefully prepared summary and the next set of priorities. You cannot step outside and see the people who are watching you. You cannot even see their planet. Before sleep, you pass the return display. Still green, you have enough supplies for the planned surface stay plus contingencies. The departure date is hundreds of days away. Nothing requires an immediate escape. In fact, leaving immediately may be impossible or much more demanding, because Earth and Mars are not arranged for your convenience. Your long stay is not evidence that you are trapped. It is part of the trajectory that made the mission feasible. The difference between a base and a prison is not whether the door opens today. It is whether the door will open when the route home exists. You survived your first sol. The return window is still hundreds of days away. Before the rocket can carry you home, the base must remain alive through every day and night between now and then. You might think the first threat to the base is a dust storm large enough to throw an astronaut across the landscape. Mars is happy to disappoint cinema. Its atmosphere is so thin that even fast winds exert far less force than similar winds on Earth. A storm can move dust, reduce visibility, reshape the thermal environment, and interfere with equipment. But it is unlikely to hurl the ascent vehicle into the next crater. The dangerous part is not a wall of air. It is what the dust does to light, heat, surfaces, mechanisms, and time. Solar energy at Mars is weaker than at Earth because Mars is farther from the Sunday. The amount varies with season and orbital distance, but even the best conditions offer substantially less incoming solar energy than typical Earth orbit. Night still arrives. Dust can settle on arrays. Regional or global storms can fill the atmosphere for weeks or months, cutting the sunlight reaching the surface. Robotic missions have demonstrated both the usefulness and vulnerability of solar power. Opportunity survived on Mars for years beyond its intended mission, sometimes benefiting when winds remove dust from its panels. In 2018, a planet-encircling dust event reduced sunlight until the rover could no longer maintain operations. Opportunity did not awaken afterward. A human habitat cannot solve that problem by waiting for better weather, while 4 people become very philosophical in the dark. Power is life support, thermal control, communications, computing, lighting, food preparation, medical capability, battery charging, suit servicing, rover operations, science, and perhaps propellant conditioning or production. A temporary reduction can force priorities. A sustained loss can turn independent systems into a single emergency. That is why NASA selected fission power as the primary surface power technology for its initial human Mars architecture studies. Fission does not care whether the sun is up or whether the atmosphere is full of dust. It can provide continuous power across different sites and seasons. Solar may still supplement a base, charge distributed equipment, or provide redundancy, but relying on it as the sole primary source creates demanding storage and storm survival problems. Now the danger has changed shape. A fission system avoids weather dependence, but it remains hardware. It must travel to Mars, land, deploy, reject waste heat, distribute electricity, and operate with limited repair options. It may be placed at a distance from the habitat, requiring cables or other distribution infrastructure. The descent plumes of later vehicles must not shower it with destructive debris. Redundancy must be real, not merely 2 units sharing one vulnerable connection. You learn the base by its power map. Some loads are continuous and sacred, others can be delayed. Exercise equipment may pause. A laboratory freezer may warm within a defined limit. Rover charging may wait. Propellant operations may slow only if the schedule contains enough margin. The habitat can dim lights, reduce non-essential computing, change thermal settings, and postpone science. Every load shed buys time by borrowing from another objective. One afternoon, a power converter trips. The base does not go dark. Automatic protection isolates the fault. A redundant path carries essential loads. Displays change color. The fan continues. You and another crew member review telemetry while Earth remains unaware of the event. By the time the first data reaches mission control, you have already confirmed the habitat is stable and begun a procedure. The failure is somewhere outside. That sentence matters on Mars. Outside means pressure suits, airlock cycles, consumables, exposure, dust, limited dexterity, and no casual return for a forgotten tool. You assemble a kit using the diagnostic tree. A crewmate verifies every item. The crew medical officer checks the excursion plan because even routine maintenance changes the base's risk posture. At the outer unit, dust has accumulated around a housing, but has not penetrated the sealed electronics. You inspect, photograph, test, and follow the approved isolation sequence. The component can be bypassed. Full replacement would consume a spare that has no duplicate. You choose the bypass. Power returns to normal configuration with reduced redundancy. The display turns green again. The base is safe. The mission is still nominal, if nominal is allowed to include a growing footnote. This is the first surface example of the rule you learned in transit. A repair can solve today's failure while altering tomorrow's. Suppose the primary power system later loses another channel during a dust storm. Solar backup contributes less. Batteries cover hours or days, not an indefinite season. The crew may shut down science, isolate modules, gather in a smaller, heated volume, and preserve only life support and critical ascent systems. That can extend survival. It cannot make absent energy reappear. And if the mission manufactures or conditions ascent propellant, power has a second identity. Electricity is not only keeping you alive today, it is accumulating your future velocity. Each hour of plant operation moves oxygen into a tank, maintains cryogenic conditions, runs pumps, and preserves the chemical potential needed for launch. A power shortfall months before departure may not create an immediate alarm. It creates a debt measured in kilograms of propellant and days of lost schedule. The crew can recover only if the production rate, reserves, and remaining time allow it. This is procedural suspense with no visible monster. The tank level rises more slowly than the calendar falls. Your mission has anticipated this. Propellant may have been completed before crew departure. Tanks may include reserve. Power may include independent strings. Critical components may be replaceable. Yet Mars rewards attention to common causes. Two redundant devices, mounted together, can share the same dust. Thermal cycle, software defect, plume damage, or badly placed cable. Redundancy works only when the backup is not waiting in the same trap. After the repair, you stand outside for a moment before returning to the airlock. The sun looks small through the visor. It illuminates an entire world and still cannot be trusted to keep one room warm without an architecture around it. Back inside, you cross the dust line. You hear the fan. You check the return display, green with one channel unavailable. You survived the first power failure. One channel is gone. The base remains alive. And now the next danger begins without pain, noise, or any sensation at all. Nothing hurts when carbon dioxide begins to climb. That is what makes it dangerous. The habitat continuously measures the composition of its atmosphere. Oxygen matters, but so does the removal of what you exhale. Carbon dioxide at elevated levels can cause headache, impaired thinking, and other symptoms before the cabin runs out of oxygen. Trace contaminants from materials, electronics, cleaning products, experiments, and human metabolism also accumulate unless the air revitalization system removes them. On Earth, the atmosphere is an almost incomprehensibly large shared reservoir. Indoors, you open a window. On Mars, opening a window is a fast method of replacing your breathable air with a thin carbon dioxide atmosphere and several regrettable decisions. So the habitat processes its own interior again and again. Fans move air through filters and beds. Carbon dioxide removal hardware captures the gas. Oxygen may be generated by splitting water. Some architectures can react hydrogen with carbon dioxide to recover more water. Humidity condenses and enters the water system. Wastewater passes through multiple stages of treatment. Sensors check product quality. And unacceptable water returns for reprocessing. The loop is elegant on a diagram. In the habitat, it contains pumps that vibrate, filters that load, catalysts that age, valves that stick, microbes that grow where nutrients and moisture permit, and sensors that can lie. You drink from the loop every day. The water recovery system does not need to recover every molecule to be useful. It needs to recover enough, at acceptable quality, while stored reserves or local sources replace losses. Even a high recovery percentage leaves a remainder. Water disappears into waste that cannot be processed. Samples, leakage, maintenance, food, hygiene materials, suit operations, and human choices. Over a long mission, small losses become cargo or mining requirements. If your base uses Martian water, another chain begins. Ice or hydrated material must be located, accessed, excavated or heated, transported, extracted, purified, tested, and stored. Martian water can contain perchlorates and other contaminants. A resource on a map is not yet a resource in a pipe. The crew does not simply trust a clear liquid. Instruments verify it. One morning, a conductivity sensor flags processed water outside its expected range. The system automatically diverts the stream rather than sending it to the potable tank. You have stored water. No one is thirsty. The problem is time. You run a calibration check. The reading persists. Is the water contaminated, or is the sensor drifting? Replacing a sensor may disturb a functioning line. Trusting a faulty reading wastes water and processing capacity. Ignoring a correct reading risks the crew. Earth can help analyze telemetry, but the crew must stabilize the system first. You take samples, use an independent measurement, inspect recent maintenance logs, and compare the anomaly with temperature and flow. Another sensor, elsewhere in the process, begins to tell the same story. The water processor is producing something outside specification. The likely cause is a treatment bed approaching exhaustion earlier than predicted. You have a replacement. It is awkwardly located behind panels that also carry unrelated lines. 2 crew members work through a procedure designed to prevent contamination and accidental disconnection. Tools are tethered even in Martian gravity, because dropping one into a crowded bay can turn a simple maintenance task into an archaeological excavation. The old unit comes out, the new one goes in, the system flushes, samples improve, the cup fills again. This repair feels more intimate than the power converter. You can see the amount of stored water on the display. You can calculate consumption. You know how many replacement beds remain. The habitat has not hidden the future in a green word. It has reduced it to inventory. Air has similar arithmetic, but the time constants can be shorter. A total loss of ventilation or carbon dioxide removal is an emergency. The crew can move into another module, use emergency scrubbers, reduce exertion, isolate the fault, or activate backup hardware. Pressure loss is faster still. Fire can poison an atmosphere even if the pressure vessel remains intact. The habitat must detect, suppress, and then clean up the products of combustion without help from an outdoor environment. Every solution consumes something: cartridge capacity, battery power, oxygen, water, filters, crew stamina, or the clean volume of an unaffected module. This is why the base contains more than one safe configuration. The full habitat is comfortable and productive. A reduced mode preserves essential systems. A storm shelter offers greater radiation shielding. The lander or rover may serve as temporary refuge. Modules may isolate from one another. Emergency masks and portable oxygen provide minutes to act. None is a permanent substitute for the functioning base. You can survive failures by becoming smaller. First you give up science, then mobility, then comfort, then parts of the habitat. Each contraction preserves the core. Pressure, oxygen, carbon dioxide control, temperature, water, power, and a crew capable of repair. The base becomes less like a settlement and more like a lifeboat. The danger is not always that one system reaches zero. Systems support one another. Water may be needed to generate oxygen. Power runs the water processor and air circulation. Thermal control protects batteries and electronics. Crew health determines whether maintenance occurs correctly. Communications help diagnose unfamiliar faults. A single power failure can therefore appear later as a water shortage, oxygen constraint, missed propellant target, exhausted crew, and deferred repair. Mars does not need to defeat 5 independent safety systems. It needs one failure to recruit the others. After the water repair, you update the inventory. 1 treatment bed remains. Resupply is not scheduled before departure because the nominal mission does not need it. A later cargo opportunity could carry more, but that cargo would leave Earth only when orbital geometry permits and would still need months to arrive and land close enough to matter. The replacement part on your shelf is worth more than its mass. It is an option. The old part is not discarded immediately. You examine whether it can be regenerated, cleaned, or repurposed. Materials on Mars acquire second careers. Packaging becomes organization. Structural pieces become brackets. Failed electronics become sources of connectors. A base with advanced manufacturing could print selected polymer or metal parts, but it cannot print every bearing, catalyst, membrane, sensor, integrated circuit, or certified pressure component from dust and optimism. Self-sufficiency is a spectrum, not a flag you plant. That night, the cup of water beside you is ordinary again. The fan continues. The red dust remains beyond the airlock. The mission is safe, but the remaining spare has become a quiet deadline. You survive the water processor. The cup fills again. But water is not the only consumable whose clock began years before you arrived. Your food may be older than your time on Mars suggests. Cargo for a human surface mission can be sent long before the crew. Meals may spend months being prepared and integrated, wait for a launch opportunity, travel to Mars, sit in a habitat, support a long surface stay, and still be needed if departure is delayed. NASA researchers have studied food systems with roughly 5-year shelf life needs for Mars scenarios, because the clock can begin well before anyone takes the first bite. Shelf life does not mean the package suddenly becomes poison at midnight on an anniversary. Safety, nutrition, texture, flavor, and acceptability change at different rates. Some nutrients degrade. Fats can oxidize. Colors and textures shift. Packaging must resist oxygen and moisture while surviving radiation, handling, and time. A meal can remain microbiologically safe while becoming less nutritious or so unappealing that the crew consistently eats too little. Appetite is part of the system. During the first weeks, menu variety helps mark days. Crewmates trade items. A favorite meal becomes informal currency. Fresh crops. If the habitat can grow them, provide food, sensory variation, and the psychological luxury of caring for something alive. Yet a small growth chamber does not replace the stored food system unless the architecture carries the light, water, nutrients, volume, labor, and biological reliability required for substantial agriculture. The first Mars crew is unlikely to survive by planting potatoes in untreated regolith. Martian soil is not garden soil. It lacks the living ecosystem familiar to terrestrial agriculture and can contain perchlorate salts hazardous to people and plants. Growing food would require controlled substrates or treated local material, nutrient management, water, light, atmosphere, microbial control, and backup plans for crop failure. A greenhouse is another spacecraft system, except some of its components wilt when offended. Stored food remains the dependable foundation. That dependence creates a hard limit in a stranding scenario. Suppose you miss the planned departure. The habitat carries contingency food, but not an infinite warehouse. Rations can stretch energy intake, reduce variety, and prioritize crew members according to medical needs and workload. Plants can supplement some nutrients. Microbial systems may manufacture selected vitamins on demand. Future missions may include more regenerative food production. None changes the basic arithmetic without enough productive capacity and raw inputs. People consume calories every day, even while waiting for orbital mechanics to improve its attitude. Food also creates waste. Packaging, crumbs, inedible biomass, human waste, and expired materials accumulate. Some can be compacted, processed, or converted into useful products. Some becomes shielding. Some remains a storage problem. On a long mission, trash competes with people for volume unless the habitat includes deliberate pathways for it. There is a temptation to imagine survival as a matter of courage under scarcity. In practice, it is logistics under boredom. You count packages, you track actual consumption, you notice that one crewmate avoids a particular meal. You monitor body mass and nutrient intake. You adjust exercise and work while trying not to let conservation become malnutrition. You prevent a small preference from growing into a health problem over hundreds of repetitions. The crew cannot simply eat the emergency reserve early because the menu has become tiresome. Those packages are future days. One evening, you open a meal that should have remained acceptable. The seal is intact, but the odor and appearance are wrong. It is isolated. Related lot numbers are inspected. Several packages show degradation beyond predictions. The loss is not large compared with the total stores, but food margins are designed with categories and nutrition in mind, not only total mass. Losing a group of meals can remove more of one nutrient or reduce the limited menu further. Earth receives the report and begins analysis. Perhaps storage temperature exceeded limits during an early uncrewed season. Perhaps radiation, packaging variability, or an interaction in the food caused faster change. The crew does not wait for a courtroom verdict. You revise the inventory and meal plan. Again, the immediate problem is solved by spending the future. The failed food will not kill you tonight. It changes how long the base can support 4 healthy people if another event extends the stay. A departure delay of days is manageable. Months require deeper replanning. Missing an entire favorable opportunity could demand survival until another mission or trajectory becomes available. And that interval is not measured by motivational speeches. It is measured by dinners. This is one reason a rescue mission cannot be treated as a last-minute package sent from Earth. Cargo has to be prepared, launched, transferred, flown, landed, and made compatible with your systems. Even if Earth has food ready, the planets may not offer a fast, practical path, and every kilogram of emergency food competes with repair hardware, medical supplies, power equipment, propellant, and landing capability. The rescue planner faces a cruel question. What does the crew need first, and what can the rescue vehicle actually deliver in time? You close the storage bay. The inventory now contains fewer meals and more uncertainty. Outside, Mars has enough carbon, oxygen, hydrogen, nitrogen, minerals, sunlight, and land to tempt civilization. Around you, none of those resources becomes dinner without a machine, process, and supply chain. The planet is rich in ingredients and poor in groceries. You survived the 5-year dinner. That sounds generous until you remember that Mars is already trying to enter the habitat 1 grain at a time. Here is the part the photographs cannot show. Mars is fine enough to enter places designed to exclude it. Dust settles on seals, radiators, optics, joints, connectors, tools, sample containers, suit fabric, and the folds where one material meets another. Wind does not need to knock you down to move particles across the site. Your own boots and rover wheels lift them. Landing and ascent engines can drive them with far more energy. Every excursion carries some of the surface back toward the habitat. The outer airlock is therefore not just a door. It is a border control system for a planet. You return from an excursion and place tools in the dirty zone. External suit surfaces are cleaned according to procedure. Filters capture airborne particles. Samples remain contained. The habitat monitors particle levels and chemical exposure. If suit ports are used, much of the dusty suit stays outside. But seals and interfaces still demand inspection. If the whole suit enters an airlock, cleaning must happen before the dust can migrate into living areas. The red line remains imperfect. Fine particles appear on a surface beyond the expected boundary. A wipe sample confirms that Mars has entered the habitat in a small quantity. This is not automatically a medical emergency. It is a warning that the control strategy has a path. Martian dust may present multiple health concerns. Its small particles can irritate lungs and may contain substances such as perchlorates, silica, iron oxides, and other components whose effects depend on concentration, particle properties, route, and duration of exposure. Perchlorates are particularly important because they can complicate the use of local water and regolith. The exact toxicity of real Martian dust in a human habitat remains an area of research. Robots do not have lungs, thyroids, or long-term occupational exposure records. The honest response is neither panic nor dismissal. It is containment. You trace the likely route to a worn interface on equipment transferred through the airlock. A brush intended for external use had been stowed too close to a clean-side container. The procedural error is small enough to feel embarrassing and important enough to rewrite the stowage plan. Filters run at a higher setting. Surfaces are cleaned. Crew exposure is assessed. The medical officer logs symptoms and finds none. Equipment receives new color coding that no one will confuse while tired. Dust is also mechanical. Particles can abrade moving surfaces, obscure cameras, alter thermal properties, and degrade seals. A pressure seal need not fail spectacularly. Damage can begin as a leak rate that remains acceptable, then increases across cycles. The crew inspects critical interfaces because time turns dust from dirt into wear. One outer hatch begins to show an irregular seal signature. You stop using it. The base has another route, but that route increases each excursion by 20 minutes and places more cycles on a different airlock. A replacement seal exists. Installing it requires careful cleaning, alignment, inspection, and leak testing. The task is familiar from training and unfamiliar in its consequences. The real planet has contributed particles with shapes and electrostatic behavior your training dust only approximated. The repair succeeds. The hatch holds pressure. The alternate route returns to backup status. A spare seal leaves inventory. The pattern is now impossible to ignore. Power, water, food, dust. No single event has come close to trapping you. Each has converted a reserve into history. This is what a long surface stay is partly for. Mars science matters, and humans can explore, select, observe, and adapt with extraordinary flexibility. But the crew is also learning how quickly a base consumes itself. Maintenance data from your mission will shape every later habitat. Dust procedures will change. Seals will improve. Spares will be rebalanced. Future crews may inherit systems that make your daily improvisations look primitive. That future is comforting until you remember that the later mission is not here yet. Your base cannot borrow a seal from a design review on Earth. As the surface campaign continues, the red line at the airlock gains a second meaning. It separates not only outside from inside, but recoverable contamination from uncontrolled spread. If dust enters life support hardware, suit bearings, electrical connectors, or the ascent vehicle, it can connect surface activity to return capability. This is how an expedition becomes a system. Nothing remains merely local. Before each excursion, you inspect the weather, power state, suit status, rover range, communications, medical readiness, and base configuration. Before returning, you plan decontamination. The exciting act of walking on Mars is held between checklists because a checklist is compressed memory from failures that engineers hope never to repeat. One afternoon, you kneel beside a dark rock exposed at the edge of an ancient channel. The geological story is billions of years old. The sample may help reveal whether water once persisted here and whether the environment could have supported life. For several minutes, Mars is not a threat. It is a record. Then your suit reports a higher than expected leak rate. It remains within emergency limits, but the trend is wrong. You stop. Your partner confirms the reading. The habitat is less than a kilometer away. The rover is closer. You do not continue sampling to prove bravery to a species watching on delay. You return. Inspection finds dust near a suit interface and a small piece of damage. The suit's isolation strategy worked. The leak never became life-threatening. The incident becomes another lesson about cumulative wear. The rock waits outside. Mars has been waiting for billions of years. It can wait one more day. Your consumables cannot. You survived the dust. The seal holds. The suit is repaired. Then one of your crewmates says a sentence no one wants to hear on Mars. One of your crewmates has pain in the lower right side of the abdomen. Pain is not a diagnosis. It may be muscular strain from suit work, a gastrointestinal problem, a urinary issue, appendicitis, or something else. On Earth, uncertainty can lead to imaging, laboratory tests, specialist consultation, observation, and, if necessary, a short trip through a health system built from millions of people and thousands of institutions. Here, the health system is one small medical area. The equipment you carried, the crew's training, onboard guidance, and experts who cannot touch the patient. The crew medical officer begins an examination. Vital signs, history, ultrasound, blood and urine analysis if available, pain pattern, hydration, recent workload. Another crewmate takes over routine-based monitoring because the medical event does not ask the carbon dioxide scrubber to pause politely. You transmit the findings to Earth. At this point in the planetary geometry, the one-way communication delay is more than 15 minutes. Even if specialists respond immediately, one exchange takes over half an hour. A clarifying question can take another. High-quality data can cross the distance. Hands cannot. The patient is stable. That buys time. Onboard software guides, diagnostic steps and flags, incompatible medications. The crew uses training refreshed during transit and surface operations. Earth reviews the ultrasound images after they arrive. No single result settles the question. The team agrees on monitoring and treatment while preserving readiness for a procedure. The words procedure on Mars cover an uncomfortable range. Medical equipment competes with every other kilogram. A complete terrestrial hospital is impossible. Drugs age during long storage and radiation exposure. Supplies are finite. Sterility is harder in a habitat full of recirculated air and pervasive dust control. Surgery can consume oxygen, water, power, medications, blood management resources, and the attention of multiple crew members. Recovery may remove both the patient and caregiver from mission tasks for days or weeks. An illness therefore affects the spacecraft. If the base has 4 crew members and one becomes a patient, the crew has not merely lost 25% of its labor. Another person may become a near full-time caregiver during acute periods. Some tasks require 2 healthy people for safety. An excursion that once used 2 people outside and 2 supporting inside may become impossible. Maintenance defers. Exercise routines change. Sleep fragments. The remaining crew works longer, increasing the chance of mistakes. The patient improves over the next several hours. The pain does not disappear, but the trend and findings support conservative care. No emergency surgery is required. Relief arrives carefully. No one declares victory too early. For 2 days, surface activities stop. The crew monitors symptoms and protects the base. Mission control reshapes the schedule. Science targets that waited billions of years wait a little longer. The medical event consumes test supplies, medication, crew time, and some confidence. But it does not alter the return date. Now, consider the same event during the departure campaign. Launching from Mars may impose acceleration, vibration, suit constraints, confined seating, and periods when medical care is extremely limited. A patient who cannot tolerate launch could endanger everyone if the vehicle must depart within a narrow window. Leaving the patient behind would require a habitat and support plan for one person, plus moral and operational decisions no checklist can make painless. Delaying the whole crew could close the trajectory. Mission medicine is therefore not only about keeping a person alive, it is about preserving enough function to pass through time-critical mission phases. Your body has already traveled through multiple gravity environments, months of microgravity-altered muscle, bone, cardiovascular function, balance, and other systems. Mars gravity provides loading, but only about 38% of Earth's. Scientists do not yet have long-duration human data showing exactly how well that level protects health. The Moon offers 1/6 gravity, but only brief historical human exposure. Space stations provide extensive microgravity data, but not years at Martian gravity. You are both explorer and missing data set. Daily exercise remains mandatory. Resistive equipment loads muscles and bones. Aerobic training supports cardiovascular capacity. Nutrition, sleep, and medical monitoring matter. The lower gravity makes some movement easier and some assumptions dangerous. You can lift a heavier object, but its mass still resists when you try to stop it. A fall takes longer but can still injure. A suit turns a minor ankle problem into a threat to mobility. Partial gravity also changes the return problem. After hundreds of days on Mars, you must launch, possibly rendezvous in orbit, then spend more months in microgravity before encountering Earth's full gravity. The return vehicle needs exercise capability and medical support. If equipment waiting in orbit has been dormant, its life support and exercise systems must awaken reliably. A machine that survived the outbound journey may need to function after a long, unattended interval. The human and mechanical timelines meet at departure. Radiation continues on the surface. Mars provides more shielding than empty interplanetary space because the planet blocks part of the sky and the atmosphere removes some particles. But there is no Earth-like global magnetic field, and the atmosphere is thin. Habitats can use structure, supplies, water, or local material for additional shielding. A storm shelter protects against solar particle events. Galactic cosmic radiation remains harder to stop and contributes cumulative exposure. You do not wake each morning feeling yesterday's dose. Instead, mission planning tracks exposure and adjusts activities. A solar warning may send the crew into the shelter. The shelter is cramped, surrounded by carefully arranged mass, and equipped to support life while the particle environment passes. Inside, 4 people wait within arm's reach of emergency supplies. The base is safe. Outside, nothing looks different. Radiation teaches the same lesson as carbon dioxide. Dangerous things do not owe the senses an announcement. The medical emergency resolves. Your crewmate returns gradually to full duty. The crew has more knowledge about the patient's condition and less of several medications. A later mission could replenish those supplies. Your mission will not receive routine resupply before departure. The base has a clinic. What it does not have is an ambulance capable of reaching Earth. You survived the first medical emergency. No surgery was required. No one was evacuated, because evacuation does not exist. The crew returns to work. Then an ordinary disagreement exposes the next point of failure. Here is another machine your survival depends on. The crew. It has 4 human components, no true spares, and behavior that cannot be summarized by a green light. Selection and training have prepared you to live and work under stress. You know one another's habits, strengths, communication patterns, and technical roles. You have practiced emergencies while tired, isolated, overloaded, and observed. Psychological screening reduces risk. Team training builds shared procedures. None transforms people into identical, frictionless modules. Long confinement creates weather inside the group. Small irritations repeat. One person closes a storage latch too loudly, another delays reports until every sentence is perfect. Someone treats shared meals as optional. Someone else uses humor exactly once too often. These are ordinary human differences, which is precisely why they matter. Mars does not need a dramatic mutiny. It needs fatigue to make two competent people interpret the same ambiguous telemetry differently during a repair. The crew manages itself deliberately. Schedules include sleep, exercise, private time, meals, personal communication, and recreation, because performance is not improved by treating every waking minute as extractable labor. Lighting helps maintain circadian rhythm. Workload is monitored. Earth-based behavioral health teams provide support on delay. Conflicts are addressed before they become organizing principles. Still, the mission accumulates asymmetries. The medical officer carries decisions no one else carries. The commander feels responsible for the whole. The systems specialist sees maintenance debt in every postponed task. The geologist sees science windows closing under operational caution. Each is correct within a different map of the mission. After the suit leak, external exploration is restricted while seals and procedures are reviewed. The geologist argues that the damaged interface has been identified and the remaining suits are healthy. The systems specialist argues that dust exposure is producing a trend and the spare inventory is thinner than planned. The discussion remains professional. It also lasts through dinner. Earth cannot referee in real time. By the time Mission Control receives a recording, the crew must already have chosen the next day's plan. You agree to a shorter excursion with a conservative route and additional inspection. It preserves science and tests the new controls. No one gets everything. That is usually what good operational decisions feel like. Now imagine the same crew after a departure failure. The mission's psychological finish line has vanished. A planned stay of hundreds of days has structure, milestones, science campaigns, preparations, a departure date, and a world expecting your return. A missed launch window can replace that narrative with uncertainty. The crew may have to survive for an interval no training schedule was built to contain. Family lives continue. Political debates unfold on Earth. Rescue proposals appear in public before engineers know whether they are possible. You become both people in danger and symbols everyone else uses. Some voices call for any rescue regardless of cost. Others question whether additional lives should be risked. Companies advertise solutions. Governments negotiate. Amateur analysts study orbital plots. Every rumor reaches you after delay, filtered through the communications plan, but never completely absent. The crew must keep maintaining the habitat while the planet that sent you argues about what you are worth. This is why psychological resilience cannot mean cheerful endurance. It means preserving decision quality while grief, fear, monotony, and uncertainty remain present. It means allowing emotion without allowing it to take command of the air system. It means noticing when one person begins skipping exercise or another repeats checks beyond usefulness. It means distributing workload when expertise has become a bottleneck. Crew size influences all of this. More people provide more skills, labor, social variation, and medical redundancy, but require more food, water, volume, power, life support, descent mass, and ascent capacity. Fewer people reduce some mass and increase dependence on each individual. If the crew splits, leaving some in Mars orbit while others descend, each group becomes smaller and must remain capable of independent survival. If everyone lands, any vehicle in orbit must operate without a crew. There is no crew number that makes the trade disappear. Your notional crew of 4 is not a prediction. It is a way to feel the constraint. 4 is enough to create a team and small enough for one injury to reshape the entire operation. Expertise overlaps, but not perfectly. Everyone has cross-training. No one can become a second lifetime specialist in every system. Autonomy helps. Software can monitor trends, suggest procedures, schedule maintenance, navigate vehicles, analyze images, and model failures. Robots can inspect dangerous areas. A base designed for graceful degradation can reduce cognitive load. But automation also adds sensors, code, interfaces, power demands, and failure modes. When a system gives an answer, the crew must understand enough to know when not to trust it. The goal is not to remove humans from decisions. It is to keep 4 humans from becoming the slowest and most exhaustible emergency resource. Months into the surface stay, one crewmate starts waking early and sleeping poorly. The cause is not a single crisis. Workload, family news, the medical event, accumulated confinement, and a private fear about the return vehicle all contribute. The change first appears as shorter conversation. Then, a checklist error is caught during verification. No one treats it as weakness. The crew adjusts duties. Behavioral support arrives through recorded sessions. Light schedule and sleep timing change. Exercise moves. Another crewmate takes part of the maintenance queue. Improvement is gradual. The intervention costs productivity and protects the mission. This is a recurring paradox of Mars. The schedule can be saved by doing less. A crew that works through fatigue may complete more tasks today and create the mistake that ends tomorrow. Rest is not outside the engineering system. It is preventive maintenance performed on the only components that can repair all the others. One evening, the 4 of you eat together beneath habitat lights. The meal is not anyone's favorite. A delayed message from Earth plays after dessert. Someone laughs at a joke that crossed millions of kilometers and arrived at exactly the right time. For a few minutes, the base is not a machine or a lifeboat. It is a room with 4 people in it. That matters because if the departure goes wrong, the crew will become the last backup no cargo manifest can carry. You survived the argument. The plan changed. The crew remained a crew, but the people on Earth who helped train you are now too far away to join any urgent conversation. Can mission control fly you home? Not in the sense familiar from near-Earth operations. The one-way travel time for radio signals between Earth and Mars varies with planetary positions. Near the more favorable end, a message may take around 4 minutes. At the far end, it can take roughly 24. A question, answer, clarification, and corrected answer can occupy a large part of an hour, even when everyone responds instantly. This delay is not a bandwidth problem. A more powerful transmitter does not make light move faster. Better communications can carry more data, improve reliability, and create alternative routes. But causality keeps its speed limit. Imagine an engine controller reports conflicting valve positions during the ascent countdown. The launch window is approaching. The crew sends telemetry and a description to Earth. Mission control receives it many minutes later. Specialists begin analysis. Their first recommendation travels back. By the time it arrives, the physical system may have changed, and the crew may already have isolated the fault. Real-time supervision has become asynchronous collaboration. Your procedures are designed accordingly. The crew has authority and training for time-critical events. Onboard systems detect, respond, and present options. Earth handles deeper analysis, long-horizon planning, model comparison, and support that benefits from thousands of experts. The mission does not reject mission control. It changes the division of labor. This affects language. Messages include context that a live conversation would develop through quick questions. Crew logs become meticulous. Video and telemetry carry the state of equipment. Teams on Earth anticipate branches and send procedures for several likely outcomes. The crew may receive a package that says, in effect, if the value is above this threshold, do A, if below, do B, if the sensor disagrees with the independent reading, stop and send these data. The conversation becomes a decision tree crossing space. Then there is solar conjunction. About every 26 months, Earth and Mars pass to opposite sides of the Sun from one another. Radio signals traveling near the Sun can be disrupted by its ionized environment, and direct geometry can become especially unfavorable. Robotic Mars missions prepare for a period of reduced commanding, simplified activities, and greater autonomy. A human mission would need its own carefully engineered communications, architecture, and contingency rules. But it cannot pretend the Sun is transparent. For days or weeks, communication may be degraded, restricted, routed differently, or interrupted depending on geometry, frequencies, relays, and design. A crew cannot schedule all equipment failures outside conjunction. So the base enters the quiet period prepared. Maintenance likely to create risk is completed or deferred. Data storage is cleared. Procedures for likely faults are loaded locally. The crew reviews medical and system contingencies. Orbiters and relays adjust plans. Earth sends messages that acknowledge an interval in which reply may be unreliable. When the link fades, the psychological distance changes before the physical distance does. Earth has always been far away. Now the silence makes it operationally absent. The crew continues. Power is monitored. Life support runs. Science becomes conservative. No one drives a rover into uncertain terrain for the pleasure of proving independence. The habitat stores data for later transmission. On the third day, a cooling loop pump begins drawing more current. The trend is not immediately dangerous. Redundant cooling exists. You reduce non-essential heat loads, inspect filters, compare temperatures, and prepare a swap. Earth will eventually want the full dataset, but Earth cannot make the first decision. You do not wait. The crew transfers the load, isolates the suspect pump, and confirms stable temperatures. The action consumes no unique spare because the pump may be serviceable, but it reduces thermal redundancy during conjunction. Exercise is staggered to limit peak heat. Some equipment remains off. Sleep areas are slightly warmer. The fan sounds the same. Everyone hears it differently. When reliable communications return, stored messages cross in both directions. Earth reviews the event and agrees with the response. Specialists identify a cleaning procedure that may restore the pump. The crew carries it out, and current returns close to expected levels. A temporary silence did not strand you. It demonstrated why a crew that cannot operate without constant Earth instruction should never be sent. Latency creates another limit on rescue. If a vehicle arrives uncrewed with replacement hardware, it must navigate, land, and perhaps travel toward the base with autonomy. Earth cannot joystick it around a boulder. The crew can control nearby systems with short local delays, but only after the vehicle survives arrival. Rescue architecture must be capable before the rescuers can converse with the situation. Communication also cannot carry matter. Earth may send a perfect design for a replacement valve, but the base needs compatible manufacturing equipment and raw material. It may send a diagnostic insight, but not the sensor. It may send comfort, expertise, software, and plans. Those are powerful. They are not propellant. After conjunction, family messages arrive in a flood. News from Earth fills gaps the crew had learned not to touch. The home planet re-enters the room as voices, images, and compressed days. The return light remains green. Soon, however, green will have to become motion. You survived conjunction. Earth is speaking again. The pump has recovered. Now your attention returns to the insulated tanks beside the ascent vehicle. The most consequential substance at your base may be a liquid you never touch. It waits inside insulated tanks near the ascent vehicle, kept within temperature and pressure limits, measured by sensors whose accuracy has been checked more times than anyone admits. It may have been delivered from Earth, manufactured on Mars, or assembled through a hybrid strategy. Part of it will become hot gas in an engine. The rest exists because no mission should plan to use the final kilogram. Rocket propellant is not simply fuel. Many chemical engines need fuel and an oxidizer. On Earth, engines can draw no oxygen from the surrounding air during rocket ascent, in the way aircraft engines do. Rockets carry the reacting materials they need. On Mars, the atmosphere is mostly carbon dioxide and far too thin to support the launch as an ordinary combustion source. The ascent vehicle carries or creates its own chemical conditions. Oxygen is especially mass-intensive. That makes the Martian atmosphere attractive. A machine can take carbon dioxide and separate oxygen, as MOXIE demonstrated, but scaling from grams per hour in a technology demonstration to the needs of a crewed ascent vehicle changes almost every practical question. The plant must run long enough. It needs abundant power. Compressors must handle dusty, thin gas. Hot electrochemical hardware must survive cycles or continuous operation. Oxygen must be liquefied and stored. Cryogenic systems must control heat entering the tanks. Lines, valves, and seals must remain clean and compatible. Measurements must establish not only that oxygen exists, but that the correct quantity and quality can be delivered to the vehicle. If methane is manufactured locally, water or hydrogen enters the chain. Water may come from Earth, buried ice, or water-bearing regolith. Local acquisition demands excavation, transport, processing, and purification equipment. The landing site must offer accessible resources which can compete with science value, elevation, terrain safety, and power considerations. Living off the land can make you dependent on a particular patch of land. Your notional mission uses a conservative rule. Ascent, propellant production, and loading were completed before your crew left Earth. The plant has continued in maintenance mode, replacing boil-off or preserving reserves as required by design. This avoids asking the surface crew to discover after landing that the ticket home is still a pile of ingredients. Even so, storage is an active verb. Cryogenic liquids do not remain cold because the calendar says they should. Insulation slows heat. Cooling systems may remove it. Pressure management handles vapor. Sensors track tank conditions. A small leak, failed cooler, contaminated line, or incorrect reading can reduce margin over months. As departure approaches, the crew performs an end-to-end status review. Tank quantities, temperatures, pressures, valve function, engine controller health, batteries, guidance, communications, structure, thermal protection, crew cabin, docking, or rendezvous equipment. No single test can prove the future launch, but together they reduce the unknown. Then a sensor disagrees. Two measurements suggest the oxidizer reserve is within requirement. A third implies a slow loss. The difference is small enough to be instrumentation and large enough to matter if real. You do not average the numbers and hope. The crew checks calibration paths, thermal effects, tank models, and historical telemetry. Earth runs independent analysis. A visual inspection finds no external evidence. The suspected sensor has shown intermittent behavior during temperature transitions. Another measurement method supports the healthier reading. The team concludes that the sensor is drifting. Concludes is not the same as knows. Mission rules may allow launch using redundant measurements and analysis. Replacing the sensor could introduce more risk than accepting its loss. The crew marks it unavailable and relies on independent channels. The return display remains green, with a condition attached. This is what mature systems often look like before a critical event. Not perfect, but understood. Now change one fact. Suppose the measurements confirm a real propellant loss below launch requirement. If the plant and feedstock remain healthy, the crew may restart production and refill the margin. That consumes power and time. Other activities stop. Cooling and processing equipment runs continuously. Departure preparation becomes a race between kilograms and days. If the production plant has failed, the crew may repair it. If the failed component has no spare, manufacturing may help only if the part is within local capability. A simple bracket is not a high-speed compressor. A seal is not merely its shape. It is a material with known behavior under pressure, temperature, and chemical exposure. Certification on Mars becomes a judgment about whether an imperfect replacement is safer than missing departure. If no local solution exists, Earth can send hardware only on an interplanetary timeline. The planned window may close first. This is the first clear route from fault to stranding. Not permanent stranding. Not yet. A missed departure can lead to an extended stay, another trajectory, or a rescue and resupply plan. The habitat may support it. Cargo may arrive. Another ascent vehicle may eventually land. But the crew has crossed from a mission executing its original architecture into a contingency requiring a new one. The word trapped begins when return is no longer available on the planned terms. The degree of entrapment depends on what remains. A healthy habitat and power system can buy years if food, spares, medical capacity, and crew health support them. A functional ascent vehicle with insufficient propellant presents a different problem from a destroyed ascent vehicle. An ascent vehicle that can reach orbit is useful only if a return stage, supplies, and trajectory await there. A rescue mission can replace some links and not others. The factory is therefore not the ticket by itself. It is one line in a chain of permissions. The real mission continues toward its planned departure. The suspect sensor remains excluded. Propellant reserves are verified through other methods. Power is stable. The crew begins loading samples and final cargo according to strict mass limits. After living beside the ascent vehicle for hundreds of days, you finally understand its purpose in the most physical way. It does not need to take your base with you. It needs to take the people. You survived the propellant review. The tank is full enough. The sensor is not trusted. The calendar becomes the next instrument. The departure does not arrive as a single day. It grows around you for months. At 100 souls remaining, the base still looks like a science station. Excursions continue. Samples come through the airlock in sealed containers. Instruments gather weather, radiation, geology, and subsurface data. The crew talks about the return in future tense. Behind that routine, the mission has changed phase. Every maintenance decision now asks whether a system must survive only until departure or through departure. Habitat lighting can tolerate a deferred repair. The ascent vehicle cannot. A rover fault matters if the rover is needed to carry the crew to the launch site. A communications problem matters if it affects the final navigation package. A medical issue matters differently when recovery time begins to overlap the launch campaign. The schedule acquires gates. At each gate, engineering teams decide whether the remaining evidence supports continuing. Propellant quantity and condition, ascent vehicle health, orbital return asset status, surface power, crew health, weather expectations, communications, geometry, navigation updates, landing site observations that might reveal dust or debris hazards near the vehicle. A gate is not a ceremony. It is permission to spend the next layer of options. If the ascent vehicle shows a serious problem at 100 sols, there may be time to repair it, send additional procedures, alter surface operations, or examine a different return trajectory. At 10 sols, the same problem is compressed against orbital mechanics. At 10 minutes, only onboard capability matters. You begin performing inspections that were deliberately postponed until late enough to represent launch condition, but early enough to allow repair. Access panels open. Protective covers come off. Components that slept through most of the surface mission awaken. Batteries cycle. Guidance units calibrate. Communications links pass data through orbiting assets. The crew cabin is checked for leaks. Each activation spends some hardware life. Leaving everything untouched would preserve it physically and preserve uncertainty operationally. Testing too aggressively could create the failure it seeks to find. Engineers choose a middle path. Exercise what must move, inspect what can be inspected, and avoid pretending that a one-time event can be rehearsed without consequence. At 70 sols, a docking camera on the ascent vehicle produces intermittent noise. The camera will help during orbital rendezvous, but it is not the only navigation source. The crew cleans and resets an accessible connection. The image improves, then degrades again after a cold cycle. Earth analyzes the pattern and identifies a likely electronics fault in the camera unit. A replacement is available in the habitat. The repair requires an excursion, careful contamination control, and work near surfaces that must remain protected for launch. You could leave the faulty unit in place and rely on redundancy. Replacing it restores one capability while exposing connectors and seals to human handling and Martian dust. This is not a choice between safe and dangerous. It is a choice between two shapes of risk. The team decides to replace the camera because rendezvous margin is more valuable than preserving an accessible unit with a demonstrated fault. The crew rehearses the task inside, using a mock interface and the exact tools. Outside, one astronaut works while another inspects every step and reads the checklist. The faulty camera comes free. The connector beneath it is clean. The new unit seats and seals. On the next cold cycle, the image remains stable. The repair has paid back an option. Not all maintenance can do that. Some actions merely choose which weakness to carry. The power system still has one bypass channel. Water treatment has one remaining replacement bed. Several meals were removed from inventory. A hatch seal has been changed. Medications have been consumed. The mission cannot rewind these facts before departure. Instead, planners ask whether the whole system still contains enough margin for the remaining route. At 50 sols, surface exploration contracts. Long rover traverses stop. Science concentrates near the base. Samples are selected for return, and selection becomes unexpectedly severe. Every rock acquired meaning through context, effort, and human judgment. The ascent vehicle sees only mass. A sample carried from Mars must rise from the surface, join the return system, accelerate away from the planet, cross interplanetary space, and survive arrival. The science team on Earth wants material from every important site. The flight team wants mass reserve. Both serve the mission, and neither can have everything. You weigh containers and review priorities. Some samples remain in a protected cache for later retrieval. Their stories will continue without you. Data, images, and measurements preserve part of the context. The most valuable material receives a place on the ascent manifest. Humans are on the manifest too, although not in those words. Crew mass changes less than cargo mass, but health and equipment do. Each person needs a seat, suit interface, oxygen, thermal control, and emergency provisions. Personal items are limited. The habitat contains objects that became emotionally important precisely because nothing on Mars was casual. A handwritten note, a mission patch, a small tool used during the first repair, a print made by a greenhouse leaf. Some come home, some become artifacts waiting in a sealed room. At 30 sols, the crew performs a simulated departure while remaining in the habitat. The exercise begins with a fault. One crew member is medically unable to perform a primary role. A surface power channel fails. Communications with Earth are unavailable. The remaining crew must configure the base, transfer to the ascent vehicle, and reach a safe countdown state using local authority. The simulation reveals an awkward dependency. One procedure assumes that the system's specialist and commander can both be in two separate locations during overlapping checks. Under nominal staffing, the timing works because another crewmate carries part of the load. With the medical scenario, the sequence creates a bottleneck. The fix is not new hardware, it is a changed order, an automated verification, and cross-training for a task that had been treated as secondary. The crew runs the sequence again. This time it closes. Rehearsal has manufactured time. At 20 sols, Earth uplinks final trajectory refinements and branches for likely delays. The launch date is not one magical instant, but a bounded period in which vehicle performance, orbital target, and return trajectory remain acceptable. Some delay can be absorbed. Beyond that, each day demands different energy or reduces downstream margin. The countdown calendar now means two things. It marks when you intend to leave, and it measures how long the original mission remains intact. At 10 sols, an unusual dust event moves through the region. The wind cannot carry away the rocket, but suspended dust affects visibility and coats exposed surfaces. Surface operations pause. Cameras monitor accumulation. The fission system keeps the base powered. Had the mission depended entirely on solar energy, the same storm would have reached into battery calculations and propellant conditioning. Instead, it creates inspection work and uncertainty about launch site optics. The storm thins. Cleaning and verification proceed. The ascent vehicle remains healthy. At 5 sols, the crew begins leaving parts of the base in departure configuration. Experiments shut down. Data transfers accelerate. Emergency supplies split between what remains in the habitat and what rides to orbit. This division acknowledges a possibility no one wants. An aborted launch before liftoff may send you back to the habitat, while a problem after ascent may make surface supplies irrelevant. You cannot place every reserve in both locations. At 2 sols, the return display turns amber during a scheduled test. One flight computer disagrees briefly with the others, then resets and rejoins. Redundancy has contained the event, but departure rules require explanation. Logs travel to Earth. Engineers reproduce the sequence in test systems. The likely cause is a known timing interaction triggered by the test configuration, not a random hardware failure. A software change could prevent recurrence, but loading new flight software immediately before launch introduces its own risk. The team does not patch reflexively. Instead, it changes the test sequence, confirms the computers remain synchronized under flight configuration, and carries a defined response if the fault returns. The light becomes green again. This is the final form of confidence on Mars. Not belief that nothing will fail, but evidence that the crew and vehicle know what to do if a known failure appears. On the last night, you walk through the habitat slowly. The room contains scratches, labels, replacement panels, improvised holders, and the accumulated proof that 4 people lived here rather than merely occupied it. The red dust line has been cleaned for the final transfer. The cup is clipped beside the water dispenser. Fans move air through filters you will not replace again. Outside, the ascent vehicle waits. For hundreds of days, leaving Mars was a future operation. Now the future has narrowed to a machine, a trajectory, and 4 bodies that must be ready at the same time. The return light is green. Tomorrow, it must become true. You survived the final 100 sols. The launch window is open. The vehicle is ready. For the first time since landing, every system that has promised a return must make that promise physical. Departure day begins before anyone sleeps. The crew has already transferred samples, personal items, medical supplies, food, and equipment allowed by the ascent mass limit. The habitat has been configured to survive without you or support a later crew, depending on the mission. Data is duplicated. Experiments are secured. Waste is stowed. The rover rests where future operators can find it. You walk through rooms that have held nearly every part of your life on Mars. The exercise equipment is still. The medical area is clean. Food storage contains contingency supplies that will remain behind because ascent performance values mass more than sentiment. The cup you used on the first Sol clips into its place. The fan continues moving air through a habitat that no longer needs to sound comforting. At the airlock, the red dust line is worn but visible. The final surface excursion is not a ceremony. It is a transfer. Each crew member enters the ascent vehicle. connects suit and seat interfaces, and confirms pressure. The cabin is smaller than the habitat. Displays show the same categories you have watched for months, but their values now belong to a machine preparing to become violent. Outside cameras show the base. From here, it looks less like a settlement than a collection of containers and machines spread across an empty plain. The power system continues to produce electricity. The habitat holds pressure. A flag, if your mission carried one, moves only when disturbed. The atmosphere offers little force, and the mission has no need for theatrical wind. Mission Control sends final concurrence, but the launch sequence cannot depend on a live voice from Earth. The planets are too far apart. The crew and onboard systems own the immediate decision. Valves configure. Tanks pressurize. Guidance aligns. The vehicle checks paths through sensors and computers. A hold can stop the countdown, while a condition is safe to investigate. Later, ignition will close options faster. The return light is no longer a summary on the habitat wall. It has become hundreds of individual states. Power available. Cabin sealed. Propellant conditioned. Flight computers agreeing. Navigation valid. Engine ready. Range clear. Although the range is an uninhabited planet, orbital target where it should be. Crew restrained. The countdown reaches 0. For the first time in human history, a crewed rocket attempts to lift people from Mars. Ignition drives exhaust against the surface. Dust erases the lower view. The structure shakes. Acceleration grows. The vehicle rises past the habitat. The rover, the power cables, and the tracks that prove humans were here. Mars does not hold you with much gravity compared with Earth, but it holds you with enough. Reaching orbit requires kilometers per second of velocity. The ascent vehicle may use stages, dropping empty structure to reduce mass. Guidance must place you into the correct orbital plane and phase for rendezvous. Merely reaching some orbit is not necessarily sufficient. You must arrive where the next link can meet you. During powered flight, an engine fault leaves little time for consultation. The vehicle can respond to certain failures automatically. Redundant systems may tolerate sensor loss or reconfigure controls. Some architectures may support engine out capability. Others may not. Abort options depend on altitude, velocity, remaining propulsion, surface assets, and vehicle design. At low altitude, a safe return to the landing site might be conceivable in a narrow set of scenarios and impossible in others. Higher, you may reach an orbit that is stable but wrong. A rescue vehicle in Mars orbit could maneuver if it has propellant and time. The ascent craft might correct if reserves permit. Every contingency is geometry plus remaining capability. The worst case is not that the rocket fails to reach orbit. The worst case is that it fails in a way no one survives. That is not being trapped on Mars. It is why return systems are tested, duplicated where practical, monitored, and treated as architecture drivers. The ascent failure that produces the title's nightmare is one that leaves the crew alive on the surface, with no usable way up. Imagine an engine controller aborts ignition before liftoff. The vehicle remains structurally safe, but diagnostics reveal damage in a component the crew cannot replace. The habitat is still functioning. Food and water remain. The planned trajectory will soon close. You are alive, sheltered, and unable to leave. That is a true stranding. Now the contingency clock starts. Can the component be repaired? Can another engine path be used? Can propellant and crew be transferred to a backup vehicle? Is another ascent system already at Mars? Can Earth send one? Will it land close enough? Does the habitat have enough resources for the wait? Can the crew remain medically capable of launch? Each yes keeps forever away. In your actual departure, the engines continue. A stage separates. Acceleration changes. The horizon curves beneath you. Not because Mars has suddenly become small, but because altitude has given your eyes a wider argument. Main engine cutoff arrives. The cabin becomes quiet enough for the fan to return. You are not home. You are in Mars orbit, moving fast enough to keep falling around the planet. Navigation confirms the trajectory. The ascent vehicle begins rendezvous with the waiting return system. If the architecture uses a single vehicle that continues toward Earth, the details differ, but the requirement remains. Ascent must connect to interplanetary return capability. Rendezvous is another chain of measured approach: communication, navigation, and docking. Its power, thermal control, propulsion, life support, seals, software, and docking system must work when you arrive. A failure here could leave you in orbit, with limited consumables and a surface base you can no longer reach safely. Distance of a few kilometers can be fatal when vehicles cannot remove it. The target grows in the window. Relative velocity falls. Sensors agree. Docking mechanisms, contact, capture, and seal. Pressure checks confirm the connection. The hatch opens. You have escaped the surface. Only now can the habitat's return light, still glowing for an empty room below, be allowed to mean something close to what you once imagined. You survived the ascent and reached the vehicle waiting in orbit. That is what happens when the plan works. To understand how the same crew could have remained below, we need to return to the one thing no repair can stop. Both planets continued moving while you prepared to launch. Why could the crew not simply wait a few days and launch whenever the ascent vehicle is repaired? Because leaving the surface and leaving Mars are different events. The ascent vehicle can place you into Mars orbit when its local conditions and target allow. The interplanetary departure must send the return spacecraft onto a path that intersects Earth at the correct future time and velocity. Earth and Mars both orbit the Sunday. A useful path is not a static road between fixed endpoints. It is a timed transfer between moving worlds. Favorable low-energy opportunities repeat roughly every 26 months, because that is how long Earth takes to gain a full cycle of relative alignment on Mars. Conjunction-class missions use lower energy transfers and often include long stays at Mars, producing total mission durations that can approach 3 years or more depending on design. Faster or shorter stay trajectories may be possible with higher energy, different propulsion, or paths that introduce other constraints. There is no single universal Mars timetable. The crucial fact is that delay has non-linear consequences. Missing a train by 10 minutes means waiting for the next train. Missing an interplanetary departure by a small amount may require more propellant to correct, a different arrival speed, or a trajectory the spacecraft cannot perform. Eventually, the useful path leaves the vehicle's capability. The next practical opportunity may be many months or roughly another synodic cycle away. That does not mean a missed window automatically keeps you on Mars for exactly 26 months. Mission designers examine contingency trajectories, aborts, opposition class options, propulsion reserves, and safe havens. The answer depends on date, spacecraft, staging, health limits, supplies, and what failed. But no engineer can negotiate with the planets. The spacecraft must pay the required energy. Suppose the ascent vehicle cannot launch before the planned Earth departure opportunity closes. The crew remains in the habitat. Earth begins evaluating options. The original return vehicle in Mars orbit may not be able to wait indefinitely. Its consumables, orbital stability, propellant, thermal systems, and life support dormancy all have limits. It might depart uncrewed, move to a safer orbit, or remain for a later attempt. Each choice changes the rescue problem. Food becomes a calendar. Spares become probability. Radiation exposure continues. The crew's bodies spend longer in partial gravity. The base's power system accumulates operating hours. The water processor uses its final replacement bed. Medications age. The habitat that supported the planned mission must now cross an interval it was never promised. The easiest rescue may be information. a repair procedure that restores the ascent vehicle. Next comes a compact part that an uncrewed cargo mission can deliver. Harder is a replacement subsystem. Harder still is a full ascent vehicle, because a machine capable of carrying humans from Mars must itself be launched, transported, landed, checked, fueled, and integrated. The crew may need to travel to it. Landing a replacement close enough is not a trivial detail. A heavy lander avoids striking the existing base and power systems, which creates separation. Precision landing reduces distance but cannot remove all risk. A rover must survive long enough to reach the new vehicle. The crew needs suits and consumables, connectors, communications, propellant standards, cabin interfaces, software, and docking targets must be compatible. A rescue designed after the accident may arrive with exactly the right part and nowhere safe to attach it. This is why rescue capability is largely designed before the emergency. Standard interfaces, spare docking ports, common propellants, autonomous cargo transfer, maintainable hardware, local manufacturing, extra habitat capacity, and pre-positioned duplicate assets are not glamorous. They turn future improvisation into present architecture. The best rescue vehicle may be the backup that arrived before the crew. If no backup exists, Earth must decide how much new risk to accept. An accelerated mission can skip tests and consume reserves, increasing the chance that rescuers also need rescue. Sending another crew may add medical and repair skill but exposes more people. Sending cargo autonomously avoids that human risk, but may limit what can be installed, and the entire effort is synchronized by orbital geometry. This is the answer to the question about a simple launch from Earth. Earth cannot respond to Mars as if distance were the only obstacle. Even a spacecraft ready on a launch pad needs an achievable trajectory. A heavy lift launch, Earth departure stages or refueling, months of transit, Mars arrival, and a landing or rendezvous system. If none is already prepared, manufacturing and integration add years before the interplanetary clock even starts. By then, the stranded crew may not need a rocket first. It may need filters next month. A rescue campaign could therefore arrive in layers. Software and procedures immediately. A fast, small cargo with critical parts if a viable trajectory and vehicle exist. Larger resupply at the next robust opportunity. Replacement ascent capability later. Each delivery extends options, but each must work. The crew's job is to remain rescuable. That means protecting health, conserving food, preserving mobility, maintaining landing beacons, keeping communications alive, and avoiding unnecessary risks. Exploration contracts. The base becomes a survival installation. Crew members may prepare landing zones, refurbish rovers, manufacture tools, and reorganize power for a longer stay. They also keep living. Birthdays occur, Earth seasons change, messages show family members aging, the crew sees Mars cycle through weather and light. Habits become culture. The habitat acquires repairs no drawing on Earth contains. A planned mission asks whether people can live on Mars for a defined time. A stranding asks whether they can continue after the definition fails. You survived the missed window scenario. Resupply remains possible. Repair remains possible. Another vehicle may remain possible. But the title does not ask whether you could be delayed. It asks when delay becomes forever. We can now answer the title precisely. The first humans on Mars may become stranded if their ascent or Earth return chain fails and they cannot restore it before the usable departure trajectory closes. They may be trapped there permanently only if the failure is irrecoverable with local resources and no later mission can repair, replace, evacuate, or sustain them before their life support, food, medical, power, or health margins run out. Forever is not a launch delay. It is the loss of every remaining path. Consider 3 scenarios. In the first, a valve fails 2 months before departure. The crew has a spare and replaces it. The schedule absorbs the work. This is a mission anomaly. In the second, the same class of failure occurs near departure with no spare. A cargo vehicle can deliver the component, but not before the planned window. The habitat can support the crew through a later opportunity after resupply. This is a stranding, perhaps a severe and dangerous one, but not permanent exile. In the third, the ascent vehicle is damaged beyond repair, no backup exists, and the habitat has lost enough power or consumable margin that it cannot keep the crew alive until a replacement vehicle could arrive. This is the path toward permanent trapping. The decisive event is not only the broken rocket, it is the mismatch between rescue time and survival time. That mismatch is the true enemy. The crew can be surrounded by years of food and still be trapped if life support has an irreplaceable failure next week. A healthy habitat is not enough if no ascent system can ever be delivered to the site. A working ascent vehicle is not enough if the orbital return stage is lost and no replacement can rendezvous. Even with all the hardware, the crew can lose the medical ability to tolerate departure. No hazard wins alone. This is the delayed truth behind every repair in your mission. The power converter, water treatment bed, food loss, hatch seal, medication, cooling pump, and propellant sensor did not take turns trying to kill you. They changed the state in which the next problem arrived. They consumed shared margin. Engineering risk is often presented as a list: radiation, isolation, distance, gravity, hostile environment. Lists are useful for assigning teams. Mars does not respect the departments. Radiation can degrade electronics and people. Dust can affect health, seals, power, and mechanisms. Power can affect air, water, thermal control, communications, and propellant. A medical problem can remove maintenance labor. Communication delay can slow diagnosis. A missed trajectory can make every consumable carry 2 more years of meaning. The trap is interaction. This also explains why the first crew need not be reckless pioneers sent on a one-way gamble. A carefully designed mission attacks the interaction before launch. Return assets arrive early. Propellant is verified. Surface power is redundant and robust. Habitats isolate failures. Critical spares are selected with mission-wide consequences in mind. Crews train for autonomous medicine and repair. Standard interfaces allow later vehicles to help. Cargo and trajectories include contingency margin. NASA's current architecture work explicitly treats safe crew return as essential while acknowledging that Mars may lack the safe havens and rapid Earth return options available closer to home. There is no way to reduce the risk to zero. That statement is true of every human spaceflight and does not by itself justify Mars. The ethical question is whether the residual risk is understood, minimized, communicated honestly, and accepted by people who are not being sold a fantasy of guaranteed rescue. Courage cannot substitute for missing engineering, nor can caution become a promise that exploration must wait until uncertainty has vanished. Uncertainty never vanishes. It becomes bounded enough to act. The title says may because permanence is conditional. Mission planners would try to ensure that any single failure produces delay, not death. That any delay still leaves shelter, and that shelter lasts longer than rescue takes. The architecture succeeds when faults remain on the left side of that inequality. Survival time must exceed response time. On Mars, response time may be years. That is the standard hidden behind the green return light. Now the answer is clear. In the mission we have been following, the ascent worked, the docking succeeded, and the return vehicle departed Mars on schedule. You are still not home. Through a window, the planet recedes. The base is invisible almost immediately. Mars becomes a disk, then a bright object against blackness. You are no longer one of 4 people living on Mars. You are 4 people carrying evidence that it can be left. The return transit repeats familiar problems in an older system. Life support must operate for months more. If the return habitat traveled with you throughout the mission, Its components already have long histories. If it waited in Mars orbit, some systems have awakened from dormancy and must prove themselves under crew load. Food remaining aboard may be among the oldest in the mission. Exercise equipment becomes critical as your body transitions from partial gravity back to microgravity. Radiation exposure continues. The crew inspects the fan. It is the same sort of sound and a different promise. On the outbound journey, it carried you toward uncertainty. On the return, it preserves the possibility of Earth. A carbon dioxide removal unit shows degraded performance. The crew activates a parallel path, cleans the first, and restores capacity. The work feels almost routine, which is not the same as safe. You have learned the spacecraft's personality. You know which panel catches, which sensor drifts after a temperature change, and which procedure omits the useful sentence everyone writes by hand. The mission's accumulated knowledge is now part of its reliability. Earth grows brighter. Communication delay shrinks. Conversations tighten. Mission control begins to feel less like correspondence and more like a room approaching at the speed of light. But Earth arrival brings its own demands. The return vehicle must target the correct corridor. A crew capsule may separate for atmospheric entry. Heat shielding must survive storage and interplanetary conditions before enduring re-entry. Navigation errors that seem tiny far away can matter at the atmosphere. The crew must tolerate acceleration after years without full Earth gravity. Medical teams prepare on the ground. Unlike Mars, Earth has recovery forces, hospitals, transport, replacement hardware, and air spread around the entire planet. The difference is almost absurd. The capsule meets the upper atmosphere. Plasma forms. Deceleration presses your body into the seat. Gravity returns not as a philosophical concept, but as weight in the chest, head, arms, and equipment. The heat shield spends itself to keep the cabin cool. Parachutes or other recovery systems deploy. The surface approaches under a blue sky. Touchdown is less elegant than imagination and more beautiful than language. Outside the hatch, people are coming toward you. They do not need a launch window. No months of interplanetary travel separate them from the hatch. No one must manufacture oxygen from carbon dioxide merely to stand beside the vehicle. The atmosphere touching their faces is the same atmosphere inside your lungs. The hatch opens. For the first time in years, air is not a product made for 4 people by a machine. You survived Mars. Now, return to the room where you are listening. Perhaps a fan is running nearby. Perhaps there is a glass of water within reach. The floor holds your body with a gravity so constant that you rarely name it. Outside, pressure comes from an atmosphere extending for kilometers overhead. If a filter fails, you can open a window. If the power stops, the room may become inconvenient before it becomes lethal. Food can arrive from a building you did not have to land from interplanetary space. Mars removes those unnoticed gifts and asks machinery to replace them one by one. That is why the first humans may be trapped there forever. Not because Mars is an evil planet, not because a dust storm will blow over their rocket, not because every long stay is secretly a one-way mission. They may be trapped because returning requires an unbroken chain of functioning systems, correct timing, healthy people, and reachable help. And Mars places more time between a broken link and its replacement than any human expedition has ever faced. But may is not will. The same chain that creates the danger can be engineered for survival. Send the return assets first. Verify the propellant. Give failures independent backups. Design parts to be reached by gloved hands. Carry the right spares. Build power that survives darkness and dust. Teach the habitat to shrink without dying. Give the crew authority, medicine, manufacturing, and time. Make later vehicles compatible with the first. Never let a departure date be the only thing standing between 4 people and extinction. The greatest achievement of the first Mars landing will not be the footprint. It will be the return. Because a footprint proves that human beings can reach another planet. A homecoming proves that distance did not take away their choices.